This is my thinking for the AP Chem exam review number 6. So they're giving us a photoelectron spectrum of an element and its ground state, and I kind of recreated it here. They're asking for the ground state electron configuration of the element and the identity of the element for part A. So I'm noticing that there are 6 different signals here on our photoelectron spectra, and each signal represents a sublevel within the shell of the atom. So I'm going to work, and I'm also noticing the binding energy in joules is on the x-axis and the number of electrons is on the y. And I also noticed they labeled each of these. I wrote the one on the far left. This signal had 647 times 10 to the negative 18th joules for a binding energy, while this signal out here to the right was only 0.980 times 10 to the negative 18th joules. So basically what that tells me is that this signal represents electrons that are easier to remove, therefore further out. So in terms of a Bohr model, with my nucleus being represented by this, I would say we have electrons in 4 different shells. So I think we have shell 1, shell 2, shell 3, and shell 4 represented by this, and I think that this would then be 1s2, and then this would be 2s2, 2p6, 2s2, 2p6, and then I think we have 3s2, 3p6 here in our third shell, 3s2, 3p6, and then since this is the same height as our other s orbitals, I would say, or subshells, I would say that this is 4s2. So this is just 4s2. So I believe that would be our electron configuration right there. So our first answer for A, I think we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then I think, I don't have the periodic table in front of me, but I'm guessing that this is calcium, because calcium would be period 4, group 2 on the periodic table. And then, so I think that's A. B, it says calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of this element. So our valence shell would be the 4s2. So here's the binding energy. So thinking about the binding energy, so here's our expression for binding energy. Energy equals Planck's constant times frequency. So they've given us binding energy, so I'm going to use this expression here, and I'm going to insert my energy in joules. Planck's constant is given off our equation sheet as 6.626 times 10 to the negative 34th joule seconds, and then frequency. So I'm going to solve this for frequency. Solving for frequency is going to give me 0.980 times 10 to the negative 18th joules divided by 6.626 times 10 to the negative 34th joule seconds. So my joules cancel, giving me inverse seconds, which is hertz. And then that answer, let's see, I want to know wavelength. So I need to use this expression to get wavelength. So that's lambda there. So looking at this expression, lambda is going to be the speed of light divided by frequency. So that's 3 times 10 to the 8th meters per second, or I guess I should have used 2.998 times 10 to the 8th, divided by our answer from our calculation here. So real quick, I'll grab a calculator and do that. Okay, I got my calculator. So 0.980 times 10 to the negative 18th divided by 6.676 times 10 to the negative 34th. So that gave me an answer of 1.47 times 10 to the 15th hertz. So now I'm going to do 2.998 times 10 to the 8th divided by that. So 2.998 times 10 to the 8th divided by 1.47 times 10 to the 15th. And that gives me 2.04 times 10. Let's see, 1, 2, 3, 4, 5, 6, negative 7 meters. So I believe that's what they're asking for here is the wavelength in meters of the electromagnetic radiation needed to remove an electron from the, I believe that is it. So there we go. There's our wavelength in meters, the energy, which corresponds to the energy needed to remove a valence electron with that binding energy. Okay, that's exam review 6. Hopefully that went well for you guys. Hopefully that was helpful.